Hello, this is a very short lecture on memory in DFT. So what's memory? What are we talking about? Very roughly speaking, it's the influence of past experience on present perception, action, and thought. So in the psychological literature and neural literature, there, of course, is a large field, very rich literature, and very macroscopic picture of that, talks about different timescales and different types of memory. And I just want to mention working memory, short-term memory, long-term memory, which I'll not discriminate here, and then ultimately I'll briefly hint at semantic memory and skill learning. So working memory is the capacity to keep perceptual, mental, or motor states, the neural states underlying such representations, available to ongoing neural processes. So that's working, to be able to use the activation of those states to make those that activation available for current processing. And so working memory arises at the time scale of perceiving or thinking and acting, so on the order of magnitude of hundreds of milliseconds, maybe up to seconds. Working memory is empirically known to have very strong capacity limits. You essentially can keep between 3, 4, up to 7 items in working memory. And what exactly item means depends on the area. It's very well understood in the case of visual working memory. For instance, you can remember properties of objects. Objects are localized, elements of a scene. You can remember features of objects, multiple different ones, colors and orientations and texture and so on. In of up to 4 or 5 objects, for each one of the instances is the number of objects that counts, not the number of feature values you need to know. And so working memory is really not really memory per se. It's really part of what the neural processing machinery needs. It's part of the state of processing. So the standard neural idea of how working memory is understood is that it is some form in which activation that was originally induced somehow by a stimulus, or we would say by a detection decision, by a decision, that such activation is then kept alive, is sustained even after that specific input that caused the activation has been removed from the sensory surface. Right? So the classical neural observation is due to Joachim Fuster, 70s. This is one of his most famous papers, in which he had monkeys act in a delayed response task. It's some kind of sorting task where they have to press a button that matches a cue, but they cannot press it right away. They have to sustain a delay, and during that delay, the cue card is removed. So they have to memorize which the right response is. And then you find that in neurons in the prefrontal cortex, these neurons then fire in this delay period, and they can sustain variable amounts of time until they make the response. There is again a huge behavioral neural literature, and this is an ongoing field of research. There's a very active research in this all the time, and it's known that this sustained activation story needs to be refined. For instance, there is something about allocating resources, so you can actually attend to different degrees, or invest different degrees of neural resources into different kinds of memories. There can vary that. And when you do that, you work memory. It's not just standing there. You also have to reactivate, for instance, memory, and this need to reactivate will come up in a moment for long-term memory. And so I'm not really addressing these issues, right? I'll give you just a very simple idea. Of course, in DFT, as you know from the foundational modules, sustained activation comes about by self-excitation. So a peak, for instance, here, self-sustained peak would remain stable even if there's no more input, no localized input, just by local excitation, and it would be prevented from spreading out by a global inhibition. We saw that. So this would be a case where there is working memory. So you induce a peak by this input, the gray line, and a nice peak standing here, it inhibits everything else self-excited, and then this peak, you remove the localized input and the peak is sustained. If you have a slightly different parameter setting, so for instance, you see the resting level is a little lower, this distance is a little larger than this distance, then if you induce a peak by input and you remove the localized input, then it will be decaying. That really means that under these conditions, when you remove input, the field goes through a reverse detection instability, so the peak is gone. When you have this higher resting level, then the field, for instance, in this case, does not go through the reverse detection instability. You could say the detection instability is, beyond zero level of localized input, and therefore the peak stays. So what we sometimes call the memory instability is this change of dynamic regime from having sustained versus not sustained activation. The resting level is just one way you go through that bifurcation. You can more typically think of the kernel parameters, like how much excitatory interaction and primarily that there is in the kernel to determine whether in one regime or in the other regime. So there's much more to be said about that, but that's enough just to pigeonhole this idea. Now, long-term memory, this slide actually doesn't belong here. Back to short-term and long-term memory, so not working memory. What's that? Well, you could say roughly speaking, we define that as a form of influence of past experience on current experience that needs an additional process, that needs something like a recall process. We often talk about cued recall, that is, you're getting some information about that past event, for instance, the gray car or the Audi that you saw yesterday, and then you can fill in the details. Or free recall, if you were just trying to remember yourself bring it back into activation memory that you had previously had. It's so the interesting thing about that is that it could take the form of episodic memory. That would mean that forming that memory could be based on a single instance of having that experience. And that is actually still not very well understood how that actually neurally works. We know that hippocampus plays an important role in being able to build such memories. The role in recall is complex. So in DFT, we don't really have a solution that's different from anyone else's solution. We use two mechanisms to have a very crude macroscopic description of this form of memory. One is the memory trace. It's a mechanism in which we postulate that any suprathreshold peak lays down a memory trace. I'll define the mathematics in a moment. We model that to be in a separate special kind of field, not a normal neural field. So it lays down a memory trace a little bit more slowly. You see it rises more slowly compared to the rise of the peak. And that memory trace conversely excites the field that it belongs to. So for instance, here you see that there was initially already memory trace at some other location, and you see a little bit of a pre-shaping influence here, pre-activation. That is, there's no external input to that, no stimulus here. It's activated just because there is a memory trace here earlier. So this reciprocal coupling of these two makes the memory trace. So mathematically, we model it by a separate equation that evolves on a slower time scale. It has a minus u term. That just means it has a time scale, but it has no self-interaction and none of that. And it's driven by the sigmoided, the suprathreshold activation from the activation field with a particular kernel, typically local. And then its role is to play, to be excitatory input into the field that it is the memory trace off. So this is a regular field equation, and the one term is this excitatory term here. So in this formulation of the model, it's always a positive number, so it's always excitatory. There's an additional implicit rule here that if there's no peak anywhere in the field, then this equation would say that the memory is decaying to zero, but that is not the case, that it would not decay. It would only decay if there is suprathreshold activation somewhere in the field. And we can actually have more refined models where the growth rate and the decay rates are separate. So this is just a postulate. It's no direct connection to neural mechanisms and synaptic mechanisms. So it's a macroscopic description. These kind of ideas have been proposed over the history of work in this area. The name memory trace refers back to ideas like that. There is some cellular information that neurons do change properties. This would be like their local resting level being increased after some firing, and there is some hint that that can happen, but there is no general understanding of that. So the effect of that is that the memory trace essentially keeps track of the history of decisions, of where peaks were formed. So if you have, for instance, through inputs here, peaks that arise at two locations here at different moments in time, there was an input given, a peak arose, and then the peak was deleted. You see the flat parts are where the inhibition goes away and the peak goes away by resetting the field with some, removing the input and inhibitor input. So over time, these different peaks arose, supraferential peaks, and then a memory trace forms. For instance, here at this location, the memory trace builds, and then at that location, a memory trace builds. And there is this interference in that you see that when there is a peak in the fields here, it builds a memory trace, and that under those conditions, under these other locations where the field is not above threshold, it then decays under those conditions. So this form of interference actually is then a model for building probability representations. So you can say how many times you have a peak at one location or another, then you could say the memory trace reflects that probability. And we've used the memory trace to account for probabilistic effects like that. So that's not very stable, and therefore, before I go there, how do you recall from memory? Well, that is the boost-driven detection instability that we looked at in the foundational lectures. So you can recreate a peak by just boosting the entire field, and you can bias the field to activate a peak over one of the locations that are pre-activated by the memory trace. We could talk about pre-shaped by having a little bit of a localized input. So for instance, you have some localized input that is overlapping here with this memory trace, or this pre-shape from the memory trace, then this peak is much more likely to be generated than that peak when you boost the field, right? And this is the slide that we had in the lecture about selection. So now back to what I just started to say. So that's not a very stable form of memory. There's a typo here in the slide. So the more stable version is ultimately Hebbian, so it's really synaptic, and there's a lot of work on that. This is a very famous area. And the idea of that is that the memory then is in the connectivity between different things, different fields, for instance, or from some sensory layers to fields. And it will be these projection strengths that we model by some kind of connectivity matrix that goes from a location X in one field to a location Y in another field, that would evolve in time. It evolves in time such that when there is both presynaptic and postsynaptic activity, that is, at a location X, activation in the field U1, it goes through a threshold here. This copied from Yulia Zanemiskaya's review paper, where she used F for the sigmoid rather than G or sigma. And again, at location 2, there would be a suprathreshold activation, and another location Y. When both of that is the case at the same time, then this dynamics would increase the memory, the synaptic connectivity, the blue arrows here at that location. And in the absence of that, there would be a tendency for the connectivity to decay. There's a learning rate that this is also a slow time scale, and there is a possibility to modulate learning of that nature. This is a dynamical, time continuous formulation of the Hebbian rule that has been more typically looked at in terms of spiking and synaptic connections. So this is how one could even think of how neural architectures can be generated first, and how maps form. The self-organized map formation, for instance, sometimes thought of being the underlying mechanism, but that's really something happening during development and early in learning, while it is also the mechanism of how memories might be formed. So, for instance, later in the lecture, we'll be looking at neural nodes that become associated with particular regions in a field by projecting excitorily, often in the bidirectional sense, to those fields. And from those fields, these neural nodes are activated, and they are then called concept nodes. And the learning of those concept nodes would arise from Hebbian learning. So that could be a model of semantic memory, which was thought of arising from many experiences, and then you extract the common properties from these many experiences. For instance, the invariant features that always arise in this context. It's, if you learn, what a cup looks like or a book looks like, you would have extracted the commonality. Those would be the only synaptic connections that over time have a chance to grow, the commonality, the invariant features of that category of objects, for instance. And it would also be ultimately connected to skill learning. When you learn to type or you learn to do arithmetic, would be the idea that in complex machinery you would be able to form the right connections that can be then be used to generate that skill. And in that sense, when the knowledge is in the connection, then Qt recall makes use of, again, some partial information, for instance, about some, in a joint representation, you would know about some subdimensions, and then you can generate a peak from in the full dimension space. And we will be talking about that in a later module when we talk about high dimension fields and binding. So if you want to think about the connection between memory trace and Hebbian learning, you could think that memory trace is like first order Hebbian learning, right? Hebbian learning is sometimes called correlational second order, in that both the presynaptic and the postsynaptic field matter, right? It's sort of picking up a correlation between those two, or covariation. And in the memory trace, it's not picking up a covariation. It just looks up whether there is a peak, and it doesn't matter how the peak came about. So it's a self-amplifying mechanism. So you can think of that as boosting the local resting level. And in dynamic field theory, unlike in neural networks, that can do a lot of work. The same mechanism that has been postulated in conventional connections neural networks, called the bias input. It's sort of the one input that's not dependent on external inputs. The one contribution to the neural activation that doesn't depend on external inputs. And it would make a very small contribution if you're input driven and you have 100 inputs and there's one number that's something like your resting level. But we saw, and I reminded you in this lecture, that by just providing a boost, you can generate a peak in a neural field, and therefore you can amplify these small differences into macroscopic states. And that's why the memory trace as a sort of order or first order Hebbian learning mechanism is really functionally significant in DFT, and that's why we're doing so much work with that. Good. That's enough as a very, very short introduction into learning.